my group mates are Sai Priya, who's doing mechanical and aerospace engineering in Chanakya University, and then Gangadhar Reddy, who's doing civil construction and sustainability, Chanakya University. So our title is on a fully functional mechanical device printing using a dual material. The hint was given in the question is printing some two-part assembly using a dual materials such as PLA and ABS or PLA and TPU, and the device we have done is adjustable hinge. So what is the main idea of our work is, by using 3D printing, we need to prepare a dual material such as PLA and ABS and PLA TPU. The device is adjustable hinge. Um, and then we have done a modeling using the Fusion 360 software. So what is the problem statement that we have found is, so the top right corner of the image, you can see a hinge, so which is used in household course. See, it has rusted and it is jammed. In humid conditions, mostly the metal hinges will get rust, right? And even if we close the doors and open the door, the noisy sound will be there, and the rough motion, smooth motion won't be there. And then and the frequent, we need to maintain it, and a replacement should also be there. And then by using 3D printing hinges, they have used only single materials so far in the literature survey, uh, so that we came to an idea of using a dual material, for separate material for a leaf and separate material for a knuckle, so that there will be a smooth flexible motion. And then the proposed solution was, we have used a polymer dual material by using FDM to print a fully working print in place adjustable hinge, so that there will be no rust, and then no extra screws also be needed, and so that the stiffness and movement can be designed, so that we can able to design as per our application, for if it is for a window, doors, or gates such as etc. It's not working. Can I operate in that? So we know in household course we usually use metal hinges. So now I want to compare between the what is the metal hinges and plastic hinges such as the polymer hinges. We know as strength, we know that metal hinges are very high, but as compared to the plastic hinges, the strength is moderate. But further, we can use, by contributing the changing in the materials, we can improve the flexibility and strengthen of the plastic hinges also. And as compared to the weight, metal hinges are quite heavy, but the plastic was very light. And then corrosion resistance is good. If it is a stainless steel, but apart from that, any other metal, there will be corrosion resistance. But if you compare the polymer hinges, there will be rust free. And impact resistance also, if you take, metal hinges have excellent impact resistance, but plastic hinges have only a model impact resistance. For that also, we need to contribute on the designing and the choosing the materials. And then chemical resistance, it depends on the metals, it depends on the material, but there will be not any chemical resistance because plastic hinges are rust free. And then high temperature performance, and metal hinges will perform excellent during in sunny days also, but plastic hinges have, in sunny days, it have only limited heat resistance. So that our main idea of work is to contribute only in the household course. And then cost is, for metal hinges it's relatively expensive, but if you use plastic hinges by using 3D printing, it will be like a more economical friendly. And then from these comparisons, we thought of doing the plastic hinges, so because it is light, rust free, and more economical. So now so far we can use it in the household course. And then metal hinges are only needed for only industries where the high temperature areas. And this is the literature survey we done based on only on the materials. So the study one is on like PLA versus ABS, which was done in FDM. So PLA means, we know each specific material have each specific properties. So PLA is like easy printing and high stiffness, but it has low heat resistance. And if the ABS means, it will be brittle when compared to PLA. And that study two, they have used TPU as compared to PLA and ABS. TPU has high flexible resistance. So we thought of doing a knuckle part in the TPU. And then study three is on classic living hinge polymers. So which polymers which are widely used now for hinges is nylon and polypropylene. And then study 4 was like metal versus plastic hinge hardware. So it is like conventional hinges. So in this, metals provides higher strength and temperature capability, but plastics offer only lower weight and rest-free operations. And then now the methodology part will be discussed by Saipriya.
Good morning, everyone. So, for the methodology, this is our part, the hinge. These 4 mount screws are printed in PLA, and the central link is printed in TPU and ABS. We have two studies. One is the PLA and ABS, that is rigid interface, and the PLA and TPU is rigid flexible interface. So, now why did we choose these materials? It is based on their mechanical synergy. PLA, polylactic acid, as my friend already told, it is very easy to print. It is rigid. It has high tensile strength and yeah, it has high tensile strength and it is basically for the rigidity and toughness. So it is its application is where basically where the hinge has to hold a rigid position. And ABS, acrylonitrile butadiene styrene, it's used for the toughness, heat resistance, and durability. It has Can I continue? Yeah. And TPU, that is thermoplastic polyurethane, it is more flexible and it has rubber like elasticity. So when it is used in the central link, it can rotate and it can, yeah, basically rotate without failing to fatigue or cracking. So next, for the validation, we have done a few simulations in Fusion 360, which will be further explained by Ganga.
So this is the model which I have designed. So these are the mounting which will be mounted to the doors, and then this is the part where it is going to bend. I have designed it to be able to bend almost 180-degree. So yeah, so here I have done the static structural analysis, and so here I have fixed all these parts. These 4 parts I have fixed, and then I have added angular moment for these the leaves, and then I have uploaded almost some 10 Newton force to this. So after getting my analysis, I have got almost safety factor of 15. So here it shows that it's a very strong material after the analysis. So this provides a high reliability and also suggests that the potential for weight and material optimization. So here I have done static displacement analysis after loading from that side. So as we can see that there is very minimum displacement. So under applied load, so the while indicates that the stable vibration behavior with no critical flexible zones. As of now, I've done this. This will be taken this hybrid.
So as of now, the summary is our project concluded what simulations we can do in Fusion 360 and how the dual material is better than a single material. The future work, we are moving from simulation to reality where we have to use the UTM machine to test the physical properties, mechanical properties, and load deflection, bending, and bearing strength, and fatigue tests and other uh, tests, and compare them to the Fusion 360 simulation results. And next part is material exploration. So now, as of now, we have only done with polymers. We are seeing materials like nylon and PP type resins. Nylon offers a self lubrication so that it helps to reduce the friction of the rotational axis of the hinges. So we can explore such materials and find the best combination for hinge life. And sustainability. Coming to sustainability, the PLA biodegrades are now they're not very recyclable, the ABS and TPU, and I mean they're not biodegradable but can be recycled. So if we go to thermoplastic elastomers, they can be more biodegradable and recyclable, so that will make the sustainable part better. That's it.
So, and these are the references. And thank you. And now I like to give the acknowledgement. So Gangadhar part was like he done modeling and designing. Everything was done by Gangadhar, and me and Sai Priya were contributed in choosing the material and device. Because in the question, they have represented to do the adjustable wrench. But after doing literature survey, a lot of people had done work in wrench. After that, we thought of doing it in a skating board, but we faced some problems in that, and then we concluded to do in a hinge, and then we both choose the material. So that's it. Thank you.
Sorry, I forgot one part in the conclusion. So we have compared PLA and can you go back? Yeah. So we have compared PLA and ABS and PLA and TPU, as I first said, the rigid, and rigid flexible. So on the findings, it's basically that PLA and TPU were found to be better compatible with each other because PLA is very rigid and TPU is more flexible. So since PLA and ABS are both rigid, the PLA and TPU have more applications in household or anywhere where you can rotate and all. That's it. Thank you.
So, and then if we consider metal hinges, there are like a lot of screws we need to insert. What we are going to do innovative, like we need to reduce the part of screws, and then that's it. Thank you.
Yes.
Yes, sir. Sir, we tried to print everything. I printed everything, but the thing was, while I assembled, I put dimensions exactly same for all the parts. But after printing, yes, as after printing, there was 0.1 mm of increase, so it was not fitting inside. So
Good morning, everyone. So we are Team 6. Uh, Myself, Geeta Shanbhag, Ramya Kulkarni, Ganesh, and Ningappa. Mahavir was unable to join our team because of some personal work. So talking about the bones as it is our project topic, does anyone know how many bones human body have? Yeah, 206. And the major parts having maximum number of bones, is it the brain, which we usually think of? Huh? Maximum number of bones in a particular area. Yeah, that's what I said. Is it the brain, which we usually think about? Any guesses? It is our hand and feet. Both contribute to half of the bone contribution, around 100 odd bones, metacarpals, carpals, and tarsals. So these having the maximum number of movements, we have maximum number of bones and joints. So this is just for facts. And the basic function of a bone, what it does is the structure, the skeleton, which gives you the um, shape, the strength, and the protection to the vital organs like brain and heart. So apart from that, it is the movement which is a very important feature. And finally, the production of blood cells, RBCs, WBCs. So our project is mimicking a bone which would be very dense in the outer layer and porous in the inner layer, which will increase the strength as well as reduce the weight. So with that keeping in mind, we'll come to the problem definition, which is variable slicing for lightweight and real world replica of bones. So using a biocompatible material. Coming to the natural human bones, which exhibits the dense cortical layer, as I said, with the porous inner cancellous structure. In conventional 3D printing, what happens is there is uniform printing, which will lead to excess material utilization, increased weight, and poor biomechanical resemblance to real bones. So, such structures usually fail to accurately replicate the bones, strength distribution, stiffness variation, and the load bearing capacity. So, there comes the need of lightweight and mechanically efficient material optimized product, which can replicate the bone and suitable for biomedical, educational, and prototype applications. So variable slicing with gradient infill density can be utilized to create a solid outer shell and porous inner core, closely mimicking the natural bone architecture, which reduces material wastage and print time. So coming to methodology, I can hand over the mic to Ramya. Ganesh, sorry.
Uh, Good morning, everyone. My name is Ganesh Malagli. I am going to explain methodology. A real bone geometry is selected and converted into 3D CAD model using a suitable modeling or scanning techniques. Uh, the CAD model is inputted into a slicing software where a variable slicing and graded infill density are defined to replicate the dense outer cortical region and a porous inner cancels region of a natural bone. We are used in PLA material. You also known polylactic acid. It is a biodegradable material also. PLA is chosen the printing material due to its biocompatibility of printing, low cost and adaptive mechanical strength. Higher infill density and solid walls are assigned to the outer layer to provide a strength, while lower infill density is used in the inner region to reduce the weight and material usage. The optimized slicing parameters are used to fabricate the bone replica using a fused deposition molding FDM 3D printing technology. The printed bone structure is evaluated for a weight reduction, structural integrity, and resumable to a real bone behavior. This is femur bone we printed yesterday. I think color are not matters.
It is solid from outside and inner infill we have porous material with honeycomb infill, which reduces the weight of the bone. So with respect to its strength, we were supposed to do the tensile testing and compression testing and bending, which for the lack of time we have not tested these points. Coming to the
Next, I will hand over to Ramya Kulkarni.
So good morning. So here we have replicated the real bone in using FDM 3D printing. So here we have used a PLA for printing this polylactic acid, which is a biodegradable material. And when we compared this PLA to other materials which we can use in printing, PLA was compatible and it was strong enough to withhold the compression and tensile for biomedical stuff. So we have used PLA material, and as ma'am told, it is porous inside, which is replicating the real bone structure. So we have practically designed, but we could not perform the tensile and compression testing due to lack of time. So it is mimicking the real bone, which can give the real strength, and like it it is like a bone. So we have printed it.
density in a remember. No. Honeycomb.
We are going to convert a diagram file into STL file. It is not possible. Not possible. We directly downloaded and
Actually, what problem we faced was like they got the file, like CT scan file from their hospital, which we tried to. No sir, like it is the printed thing from online.
Could not segment it actually in that short. No, we did that infill pattern density. I'm not sure, but as what it was printing, probably 40% of it would be. Correct. Yeah, this is. Yeah, the tensile strength is little uneven surface on the top, so there is a high probability that the joints might have breaking capacity. No, no. Yes, yes. We need to increase it. Huh. Basically for educational purposes, we make these models, but not for having getting tested with us on strength basis. So, educational model. So, yes, yes. Thank you, everyone.
Good morning, everyone. We are group number one, and our project topic is parametric investigation of binary inspired layered structures for improved mechanical performance. And the topic given to us was to uh, make porous structure for dual purposes. Now I hand over the mic to my team member Karthik. He will introduce to the introduce the team members.
Good morning, everyone. My name is Karthik Bioka. First of all, I would like to thank you, IIT Dharwad and Professor Somshekar sir, for giving us this opportunity. Our group members are Ramit Singh, Chhattisgarh Swami Vivekanand Technology University, Bilal, and Saurabh Kumar from the same university. Himanshu Raj from Darbang College of Engineering, Bihar, and Karthik S. St. Albert's College, Ernakulam, Kerala, and myself, Karthik Biolika, Kaligna Karnataka Institute of Technology, Coimbatore. Thank you.
Good morning, sir. Good morning, everyone. As we know that recent scenario is basically designing part is nature-inspired texture patterns, and basically all the designs we are taken from the natures. We see a lot of patterns, like you can see the tiger's skin, and then we can see all of the skin. So we are basically inspired from the nature and designing something. So in our case, we are going through a lot of sir, this is literature. We can show in the next slide. So despite growing interest in tree-inspired and hierarchical layer structure, existing studies for primarily focusing on demonstrating novel geometries or reporting overall mechanical performance, limited attention has been paid to understanding how individual geometric patterns parameters such as branch inclination angles, layer spacing, and members thickness and number of layers govern the deformation mechanism and energy absorption behavior. Moreover, many studies lack a comprehensive parametric framework that correlates pine tree inspired architectural features with key mechanical indicators such as stiffness, stress strain response, Poisson's ratio, specific energy absorption. The absence of such systematic investigation restrict the ability to optimize design for target applications. Therefore, a clear research gap exists in establishing structure properly relations for pine tree inspired layered system through detailed parametric analysis. Here we in literature we find this kind of structures and we choose pine headed structure, and we are wearing the layers, and we are basically constant the dimension and the layers will be changed, and the next thing will be discussed by Ramit.
Good morning, everyone. So, in the recent literature, this paper was published last week only in a reputed journal. So, they have studied this pine head inspired structure and two others, TCH and spearheaded. They found that shock absorption capacity of pine tree inspired structures is the best. So, but they have taken the similar layers. The dimensions are same for all the layers. So, we in our study, we have done a parametric analysis, as it is clear from the title. So we have varied the number of layers. We have kept yeah. First of all, these are the objectives. The main objective is to design a bio-inspired layer that we did from the pine tree inspired structure based on pine tree branching architecture. So we have taken all the dimensions, the angles remain same for all the layers, but we have enlarged it. Second is to evaluate. Yeah. Yes. Yes. Sir, these are different, sir. Sir, the basically in pine tree, there are, we can see two triangles. So we have kept the angles same, but we have varied the dimensions. So the shape remains same, but the length varies. So basically, our initial the application of this part was to make a shoe sole that will absorb the shock. So we have to find out how many optimum layers of pine tree inspired structure we have to keep so that the shock absorption is best and the compressive strength is also best. So the second is to evaluate the stiffness, deformation mode, stress distribution under compression. The third is to quantify energy absorption capabilities that we were supposed to do using the drop weight test. And the last is to propose design guidelines. Yes, yes. If we would, sir, that printer was not working, sir. We were told that is having two nozzles. So if that printer would have been working, so in one we proposed to put TPU material. Yes, sir. Sir, actually our application part was shoe sole. So no, sir. That was the novelty of our study, sir. Sir, initial application was yes, yes. Sir, but in our case, the application was shoe sole. Sir, actually, we tried around 20 to 25 times to print it using the top layer using the TPU material. But the TPU was not sticking to the 3D printer bed surface. Maybe due to the temperature variation or some other issue. We tried around 25 samples, but we were not able to make it. So this is the methodology part. So we designed the models in AutoCAD, the 2D and 3D models. So the dimensions for each specimen were fixed. The length and width are 50 mm and the height is 30 mm. Next, we printed it the layer wise. In one case we kept one layer, in second case we kept two layers, and in the third case we kept three layers. And also we printed one standard specimen that is the presently how shoes are made. The bottom layer is very thin, of a very hard material, and the top layers are very soft. It is having only 2 layers. So we printed it using layer wise material. We defined the material and we printed it. Then specimens were 3 specimens for each configuration were printed. Total of 9 specimens for pine tree inspired and 3 specimens for the standard specimen, so that we can do the comparison with the standard test. Then we assembled using a silicon based glue. Then this part we were not yeah, sir, it will matter, sir. Yeah. Yes. So initially we thought that we will print, it is divided into 3 layers. We will use total three configurations, that 3, sir, and 1 standard specimen. So we have made 3 samples for each specimen, so that we can make the error bars while we do the test experiments. Yes. And the yes, sir. Initially, we planned to do that, sir, but we were not able to print. Initially, we thought that we will keep it in 4 layers. The bottom layer will be of carbon fiber. Above that will be of pine tree inspired carbon fiber, and above that will be the similar structure. Yes, TPU plus PLA blended filament we used. The 20, no, sir, it was available. 20% TPU and 80% PLA was there. That gray one is, yes, carbon fiber we used. Black one is carbon fiber. Normal FDM, sir. Yes. So after that we have planned, our plan was to do the compression test, and finally we will study the displacement fields using MATLAB, sir. Yes, sir. These are the designs. In first one there is only 1 layer of pine tree inspired structure, and on the right side is the 3D model. The second is 2 layers, but in all the cases you can see that the width is 50 mm and the height is 30 mm. In the third case also, this is the 3-layer structure, 2D and 3D. So this is the 3D printing that we have done. So Himanshu will explain the details. No, sir. Sir, but we have planned to do that, sir. Yes, sir. Yes, sir. We'll do the simulation in ANSYS. Yes, sir. Okay, sir. Yes, sir. Yes, sir. So this is the 3D printing part. Himanshu will explain.
Good morning, everyone. This is our top part. It is printed from TPU plus PLA at honeycomb. Its infinite density 30%. This is our top and bottom part. It is printed from carbon fiber. Its infinite density is 100%.
So the first one is the standard specimen. So we have put 9 marks on that, so that while we are doing the compression test, we can use the image processing to study the displacement fields at different points. Second one is 1-layer structure. Sir Karthik will show the dots, how we are place the dots in the specimen, so that we can study the. Sir, whitener we have used. Yes. So because in this part will fail differently, and this will have a different deformation, and this part will have different deformation, and it will not deform linearly. It will. Sir, the layers will not have that strength, sir. That is why we tried to print it that way, sir. The first specimen that we printed, so it was in horizontal placement. Sir, it is in the lab, sir. We forgot to bring it, sir. It was not able to withstand the load, sir. By hand only it was breaking, sir. We tried to print one sample using that. The next slide. This is the 2-layer specimen and 3 layers. Karthik, go and show all the 3 specimens. Yeah. Yes, yes. So initially, sir, we thought that these 2 layers we will print using carbon fiber, and the this layer will be printed using TPU material. That TPU material, white top one. So it is a soft material because we are yes. So that the shoe top part of the shoe sole is soft and the bottom part remains hard, so that it will have dual applications, the weight reduction, and it can be used on the hot surfaces, and it will be comfortable as well. Sir, these are the references of the study. Bye. Yeah. So the first paper is the main paper that we considered. It was published in Frontiers in Materials, and others are the reference paper from that only. So thank you. The future work will be explained by Saurabh.
Did anyone heard about topological optimization? So the main topological optimization, what it did is when we draw something like 3D model, and we go through the software, and then topological optimization, what it does is the stress point where it is 0, it will remove automatically the material. But when we are going for the practical applications, what happened, that design is not feasible to create, right? But when we talk about the 3D printing, in 3D printing, whatever we design with support structure and something, we can easily draw that drawing. So the topological optimization is one of the field in the future work where the design we made, we have to tested it, and then the best sample we are going for that design, going for the topological optimization, and the further weight reduction is there where the stress points will be 0. So in that way we are minimizing the weight as well as the so that one is our future work. Thank you, sir.
So a very good morning to one and all present here. So today we are planning to present our project title Investigation of the Ion Transport Mechanism on Patterned Electrode Geometry for Supercaps Application. Myself, Anis Fatima, and these are all my team members, Jyotika, Sharmila, and then Abhishek. And so this is our problem statement, that how does electrode geometry, solid versus lattice versus pattern design, influence ion transport and energy storage performance in supercapacitors, and this is what we are gonna address today. So now I hand over session to Abhishek.
Good morning, everyone. My name is Abhishek. I'm aeronautical engineering second year in KIT. I give you a little introduction and basics briefs of my projects. Here, supercapacitors. It is likely similar to lithium-ion batteries. It a rapid change in natural, physical, and biological systems. Supercapacitors are widely used in very so many sectors like automobiles and in defense sectors. It is very efficient because its charging and discharging rate is very fast, and it can be uh, used a very long time. It means it is very reliable. Whereas lithium-ion batteries, it can't withstand for so long, and it is based on its electrodes are like built how can we say it based on its the distance of electrodes. It is in upcoming technologies and current technologies. It is very it is very too short, and the fillings are patterns. We researched on patterns and geometries of that electrodes in the defense sectors for uh, launching of rails and other. Actually, it is used for rapid current discharge and charging. For the from that source, we can directly apply for the like in electric buses. We saw that recently in China, they used uh, they used a lithium instead of lithium ion. They used the supercapacitors because they give bit long duration of power, and it can be charged uh, instantly. And in cars, they are used for electrical stopping brakes. And in defense sectors, as I told, it is used for launching of missiles for instant. It can throw the missiles up to 100 miles vertical lifting. It can be used for direct yeah, ejections. These are the applications, and the fully deep technology is told by members.
Good morning. Myself, Jyotika, PhD scholar. I'm doing VIT Velu. And continuing from the introduction, I like to give a brief intro about types of supercapacitors. First, these supercapacitor, also known as electrochemical energy storage device, and it known for their high electron density, energy density, and it has a faster charge discharge capability, and it has a long lifetime. And batteries also we can use for energy storage, but while charging time it will be more for batteries compared to supercapacitors. And also based on performance, supercapacitor better than batteries. And Based on the application, the supercapacitors are used in portable electronics and electronic vehicles like this. It has more applications. And the capacitors are it connecting bridge for conventional conventional batteries and conventional capacitors and batteries. And these are the main types of supercapacitors like EDL, electrical double layer and pseudo capacitor and hybrid. First, this electrical double layer is directly getting charge from the electrode layer, and these supercapacitor high redox reaction and it has high capacitance. And this hybrid, it combines the both mechanism of EDLC and pseudo capacitor. And in this slide, it explains the types of supercapacitor and what kind of electrode materials we can use. Like carbon nanotubes, activated carbons, graphene, conducting polymers, and metal oxides. These are the electrode materials we can use in supercapacitors. Particularly, these carbon nanotubes are having high mechanical strength and high conductivity. And these activated carbons are cost effective compared to other electrode materials. And compared to others, graphene has high electron mobility and high conductivity. And then it comes to conducting polymers and metal oxide are having high capacitance compared to other electrode materials. And here we are going to see how it enhances the supercapacitor performance. The supercapacitors mainly have three components like electrode, electrolyte, and a separator. First, electrode. This electrode is like heart of the supercapacitor. Like without this, it can't work. And mainly the electrode performance based on its electrode surface area and it porous and composition and conductivity. Then it comes to electrolyte. This electrolyte is the medium it placed between the electrode, and here the different types of electrodes are used: aqueous, ionic liquids, and organic liquids. And it comes to separator. This separator is used between two electrodes to reduce the uh, and okay, based on its permeability and stability, we can go for by optimizing these three electrode, electrolyte, and separator. We can enhance the performance of supercapacitors.
So now let's discuss the objective of the work. So the first objective is to design and print electrodes using different electrode geometries, and then to correlate the type of geometry, like for what type of geometry, like geroid, and then composition means in terms of material. Yes, sir. So for each geometry, what performance, like specific capacitance and ray capability, cycle life, we can uh, find out. And then and finally, after fabricating the electrode, we can further, if the based on the performance, we can add the composite by tuning via nanostructure creation. For this kind of purpose, we can use additive manufacturing. And next slide we will see how we can use additive manufacturing in supercapacitor. So first, by the advent of additive manufacturing, we can create a porous and high surface area electrodes, and then also we can create the interdigited patterns, like this kind of patterns. This is fingertips patterns. This is one electrode and this is another electrode, and then which enhances ion transport. And the next one is we can directly print the conductive materials, and then this also compatible with flexible substrates, and which can be used in wearable and micro devices also, which can also be used in implantable devices also. And then which this also enables multi-material printing, that composite kind of. And then we can immediately prototype by advent of additive manufacturing. So by simple electrode, so these are all the electrode that we have obtained. We just Sir, as for the electrode, we don't need the dimension and all. It is one by one also, it is enough. But the active material which we are using is what is improving the electrochemical performance. So this we have printed just to show how the geometry plays a very crucial role in electrochemical performance. So we have took these kind of patterns, that rectilinear, honeycomb, gyroid and concentric. So these are all the infill parameter that we have used to print this. So this is a rectilinear pattern. This is a very straightforward pattern, and then normally for in FDM modeling they use this only because this is easily printable, and also it has good mechanical stability. But since you can see, this is a more grid like structure, and then if the ion transport in this structure means the sharp this will allow, this is straight filament, this will allow the ions to turn and make the direction very randomized. And then if you take honeycomb structure means honeycomb is contains more hexagonal channels where ions can easily penetrate inside and can travel. And then if you take, this is gyroid, uh, gyroid is like very much uh, good in structure, as well as it forms a continuous network. I'm not sure if you can see, but it forms a continuous structure, so that ions can travel continuously without any change in the direction. And finally, this is concentric pattern. But we can see this has a circular loop and it is very closely looped. If the ion penetrates inside means it is just restrictive. Like why I kept this means, the if we are fabricating electrodes by using this means geometry also plays a crucial role. If we use this concentric type of means, the ions cannot go very interior to this. So for ideal high rate supercapacitor device, if we are aiming to fabricate means, we have to go for gyroid kind of geometry. So the geometry plays a crucial role. So these are all some of the literatures that I have come across. So the first one is honeycomb, gyroidal and rectilinear. So by using honeycomb, they have used a honeycomb pattern for MnO2 and CNT, and they have created 3D porous network, and they have also obtained a very much good capacitance like 324 farad per gram at current density of 0.5, and then energy density and this is the capacity retention. Even after the 5,000 cycles, they have retained specific capacitance of 324 farad per gram, that is 100% of the retention. And then the gyroidal pattern, they have used the gyroidal pattern in graphite foam. They have used a DLP based DLP method for printing this. And they have obtained a volumetric capacitance around 3.2 farad per centimeter. And another one is rectilinear infill. They have used rectilinear infill, that they have used that infill percentage will be there 20, 30, 40 percentages, and based that they controlled that one and tried to come up with the results. And it is proven that 40% of the infill rectilinear sample exhibit 4 times the capacitance than that of the 20% infill. So the infill parameter also very much important in this geometry, infill parameter. Yes. Yes. Printing geometry. Yes. Yes. Like what I will say is we have to check the both. Based on the literature, the geometry is also playing a good role in this. Yes. Morphology is also important actually at a nanoscale level. Yes. Okay. Yes. Sir, but if we look at that, they are changing the infill parameter only. The patterning itself. You're asking about this literature? Yes, sir. They have changed a lot of materials, but what I got is this paper. They have used this material. They might have tried using. Ah, yes, sir. So now the proposed methodology will be explained by Sharmila.
So the proposed methodology is by gathering 10 gram of PLA powder in and 5 gram of PE in 300 ml of ethanol, and we dissolve it in and we dissolve PLA next step, that is taking 10 gram of PLA in 300 ml of ethanol for at 50 to 60 degree centigrades, and homogeneously mix it for 2 hours, and we mix PEG along with it, and we filter and dry it to filter out the impurities, and we extrude it like a filament, and we go for printing in the FDM. And the electrochemical measurement techniques which we use is the cyclic voltammetry, the galvanostatic charge discharge, and the electrochemical impedance spectrum. In this, we will analyze the aerial capacitance first, and then we'll go for the charge discharge cycle, and we'll check the cycle stability also using that electrode, and we will go for the impedance for the geometries we are fabricating. So the fingerprinting characterization, we'll be using like powder XRD first, and we'll be going for Raman analysis, FTR, and SEM, EDAX, and BET analysis. And for electrochemical, as said earlier, we'll be using CV, GCD, and EIS for the electrochemically how it is active to check that. So this is the conclusion. So electrogeometry plays a critical role in governing like ion transport and charge storage behavior in supercapacitors. So pattern in lattice-based geometry provide an enhanced electrolyte accessibility and reduce the ion diffusion pathways, and we can actually regulate the ion diffusion pathway. That is the main motive of our whole research. And material, and the key, and by this we are looking to scale and do a fixable kind of device.
So I'd like to tell that in our future, we are like to go with our proposed methodology, and also to test the electrochemical performance of the fabricated electrode. So thank you. Sir, we can use PLA as a filament, and we can use whatever the conductive material to improve the conductivity as well as specific capacitance.
Or we
Thank
could
you.
go for the LPBF way of fabricating the electrodes also, which is much better and conductively much better in that. Mm.
Okay.
Share screen or share only screen too. When you transfer the file, then zip it, directly zip it and upload it to the because it's hidden sheet.
You are good to go.
Upload it to happen.
Very good afternoon, everyone.
Can you please use the mic?
I'll use it in my just actively after the
Because we are recording. You can use this also, no problem.
It's okay. Only for the first 3 minutes. Thank you. Very good afternoon, everyone. I'll just start off with an activity. Those of you who are comfortable might as well join in. So I'm gonna put my wrist and then the other one. Place my right arm over my left. And then the brain, which you'll find. I'm not able to shift to where it is to go. Yeah. There's a brain. Now, let's go to the lobes. There will be frontal lobe, parietal lobe, temporal lobe, and if you place your arm a bit away, you'll find the occipital lobe going behind you. Now, here's the, because this is going to come in the presentation in a while. The left side, in my case, the left side of the brain will control the right side, whereas the right side of the brain. The right side of the brain can control the left side of the brain. Now, let's say there turns out to be some or the other neurodegenerative disease or any mishaps, and the left side of the brain loses its what happens? The right side does not function properly. Let's say the same happens with your right side. Now, the left side does not function. Let's say some mishaps. and your spinal cord is injured, then what happens? You get to do nothing. And that's the case with upper limb high level amputees, which brings us to the nudging need to design and additively manufacture a risk module for assistive self-feeding devices. And probably we could call it Rehab Win Private Limited. Now, okay, this is Group 5 PhD from SSNC. As they've already looked at the product statement, I would like to mention what we are, trying to solve at present. A minimal viable product for upper limb amputees and individuals with upper limb impairments due to stroke or spinal cord injury. Now, two aspects we intend to provide solution to this model would be to consist of a linear actuator to reduce the strain. If you observe, the user has to lean forward, which might as well cause a strain. In order to reduce the strain, a linear actuator, if at all it's going to be installed in a part of the arm, then the length of the arm, right when it's going to come closer to the user, might as well increase, which will be an added advantage for the user, and thereby, there's also a question: what if it's going to cause harm to the user? What if it's going to hit them? Now that's when we implement reward vision followed by ADL and other algorithms. The second part of the module will consist of the risk module, wherein for now, it's just going to be a risk-like module consisting of two components or two components. One would be a basic spoon, the other would be a slider. Let's envision a plate. We got food, fortunately. And then there's this need for us to grab and eat, which is possible because we use the, let's just say, the low part of the arm. In case of individuals who have issue with their upper leg, do not what if only a spoon is given and only if they get to control it using a robot arm, how effective could it be? How productive or you get it. So that is what we are trying to solve. And the future scope of the spoon could be a shape changing spoon, which is made of PET, inspired from Kerry's spoon. The paper will be listed. Sorry, one. Yes, the shape change spoon. It could be PET, made of PET or TPU. And this entire spoon, if you look at it, there's a ring actuator, flexible boot, and carry gantry sheet. Now, this carry gantry sheet would expand and compress, which is all done through the mechanism. Now, let's say I've got an object here, this one. It's wood. Let's just have this wood. I need to pick it up. It's going to expand and then compress, and I'll be able to pick it up. Now, this is not the case with a normal metal spoon. It might break down. It might not be even possible to pick it up. Now, when I'm going to use this, there's a disadvantage or the limitation is I don't get to lift or pick up liquid items. That's when we need two or more such components being a part of the risk module. Few more aspects about the shape changing spoon, and what we see over there is two necessary attributes. It would be to make sure all the components are made of silicon in order to avoid any severe injury during mishaps. And second one would be the slider, which we just saw earlier, being made of temperature monitoring material. Sorry, I was wrong. Temperature changing materials in order to monitor the temperature. Now again, random things and situations lead to random outcomes. Caveman made fire accidentally out of the friction of rocks. In my case, this cable came across this particular module while going through obviously YouTube. And this was a wrist module consisting of fingers. Now, an interesting factor is that the fingers are not fixed. They get to move around. They get to be, the orientation gets to change. And I do not, at present, I do not have a solid paper to state it has been utilized in other self-feeding, devices. But there is a GitHub link, and to be even more precise, the Previously, we saw an instrument, a device, which was OMI3, helping the user to feed themselves. Now, they had kept their movements limited, or for that case, just one or two. And the reason being is, if a wrist module is integrated, the only aspect which will be, cutting short on might be safety. So to develop a wrist module, it would mean to be multifunctional at the same point, making sure safety is at most priority. Um, yeah. Now this is the minimum viable product, wherein they've used an MG 996R high-top servo and SG90 servos. As said, that's the phone and that could be slider. Overall, the basic logic would be the servo motor rotates 0 degree, 180 degrees. Let's say 0 degree, the spoon comes into order. 180 degree, the slider comes into order. And I get to basic logic, we get to decide which one is going to be used and which one is going to go out of functioning. Now, if I'm going to integrate it along with a robot arm, that's where the spectrum becomes broader. Now, this is just a basic clip or how I integrated a robot arm earlier. It's not that clear, but the components are present, followed by which the claw would open, and a safety mechanism has been implemented in it. Now, if you observe, this robot arm was made out of the functionality was to use an SAMG in order to provide the access to the robot arm in itself, which would provide the access to the movement of the robot arm, until which the user does not get to move it at all. That was a safety precaution, followed by which force sensor and joysticks have been utilized to control the movement of the robot arm and the opening and closing of claw. Yeah, few other aspects which would come under it would be pressing the force sensor in order to lock the positions and unlock the positions, or clicking the joystick in order to open the claw. Yeah. Yeah, just the basic components and that we used. I'll just skip through these. The electrode placement, tibialis anterior. So overall, what we're looking at is to develop a wrist module, which is multifunctional and at the same time not compromising on safety. Now again, what I've got in place is just a minimum viable product. How can it be, its usability, how could the usability be expanded or enhanced? And that brings us to future work, wherein this is a paper which is quite interesting, meta arms, wherein robot arms, which we get to control using a feet. So you don't have to be a hand physically yet. If you are fine with, if you're going to remapping the approach to control these arms using a feet, which we don't use much so, and with the help of haptic feedback. Now, how is this going to be useful? Would be to develop a shoe-like model, wearable controller, and with pressure or motion sensors to translate feet gesture into commands for user and to utilize lower limb functionalities. The second one would be for stroke victims, wherein I do not get to move much. My arms are laid down. I might be able to lift my wrist a bit, but not. It's not sufficient to do everyday activities. Now that's where we come into the need to control any equipment or any robot arm using finger joints, and this is a potential future scope, followed by which EEG, brain computer interface, for acute stroke patients. Now, EEG or brain computer interface is certainly into existence, and we get to order it from Amazon by just thinking about it, which is a different episode in itself. But in this particular paper, they had asked around 50 of the participants to do a particular activity. First one was instruction based. They were given cues to imagine. Now again, not to pick up, just imagine left or right hand grasping onto something spherical. Second one, motor imaginary phase, wherein a video was played for them to be guided in order to, grasp a spherical object in the right or left hand. And the third phase was the rest, do nothing. Now again, remember when we said the right side of your brain controls the left side of the body? This is where it comes in. Now these are the electrode placements, wherein let's just say this is left. Is it left? Yeah, it is left. This is right. C3, odd numbers to the left, even numbers to the right. Now, C3 and C4 electrodes will monitor your motor cortex, basically your movements. Now, the readings from these electrodes were alone taken into account, followed by which analysis were done. This jiggling entire waveforms you see is the actual EEG signal in itself, which when processed and few spectral analysis gives us these two outputs. Motor imaginary for right hand, motor imaginary for left. Yet C3 is left or right. We know it. C3 is right. So motor imaginary for right hand is higher, but C3 is for right side. Why is it higher in the left hand as well? This could be caused in few cases when the user is by all means right-handed or utilizes their right hand way more than usual. Now again, that brings me to the end of the discussion or the presentation of my topic, and I would like to end by stating a wrist module would be highly multifunctional and effective if we make sure safety is our top priority. The reference basis, and thank you for your time. Also, I would like to thank Vikraj sir and Prashant sir. They have helped me in getting the components and getting work done, and also.
So, what is your component? The printed ones?
They're very printed, but I've only tested them. I have to glue them, so.
Okay. Well,
It's like that.
so with Raj, I think just put the group names and then put the all the parts here so that we can see. Yes. Because this may be group. Just before VAT. That's it. You can keep it like that. Make sure that group name you can put the paper. You can keep the paper. We just want to see how accurately how to prepare this component. Because your effort matters, not the final. Marker. So finalize the Can I get one? Maybe meanwhile, next thing can start later. So make sure all the component, printed component, you should put here, make sure your group name here. So it will help us. That's okay. So this is how the change. Second, at least one day they have. This they have attended one. So how many of them they create? So at least one day they have. But this Bharat, that's a big one day. They are not one part of them, one single. Then anyone who knows like a text, I only attended one session. Petros.
Good morning to all. Myself Srikant Bade and my teammate that is Mohammad Shavi Kumar. We are research scholar from this college only. Our topic is that is a design of a bone scaffold with the mechanical properties matches to cancellous bone using additive manufacturing. That is a formal definition is cancellous or trabecular bone is a highly porous, lightweight structure found at the end of the long bones, such as that is a femur. It plays a vital role in load transfer and energy absorption and structural support. In orthopedic applications, bone scaffold are required to replace or support damage. That damage is due to the age matter or and due to the accident, and that damages cancellous bone. Conventional solid implants, conventional means that is a parts made from the traditional methods, often are much higher stiffer than the bone, leading to stress shielding and bone resorption. Hence there is a need for porous bone scaffold design that geometrically resembles the cancellous bone. Additive manufacturing enables the fabrication of complex porous structure with controlled geometry. FDM based additive manufacturing using PLA, that is the PLA is a biodegradable material that offers a simple and accessible approach to design and fabricate femur inspired porous scaffold for preliminary biomedical applications. This is the methodology. We reviewed the that is a literature on cancellous bone structure and porous scaffold design. We selected a femur inspired geometry as a reference model and designed a porous lattice based scaffold using the CAD software, and control the geometry parameters such as pore size, that is the thickness and porosity. Selected PLA polymer suitable for FDM based additive manufacturing. We planned that is the printing process using the slicer software and generate the G codes and fabricate the scaffold using a Bumble PS1 FDM 3D printer. The next part will explain. Ultimate.
So about the bones, bones are not the regular structures. Bones are actually some composites, and their structures are different. We're having nano, micro, as well as macro structures. Another is viscoelasticity is there. It is the an anisotropic, and usually we can say if we go for the 3D printing, we may require the FGM. It's a kind of functionally grade material. This may be required. Another is bioactivity is also there. So material selection was crucial for us. In case of polymers, the very first priority we will be giving for PEEK, that is polyether ether ketone, due to its mechanical stiffness and mechanical characters. And but we are having the PLA that is easily available, so we chose the PLA one because that resembles more into biological properties. So going to the next slide. So we use actually bamboo PS1 FDM technology. The model was simply available on the open source websites. We can get it easily, and we simply sliced it using the bamboo bamboo software, slicing software. Can you go to the next? Yeah. So the upper portion are actually the screenshots from the printer, and below are the real. Actually, I wanted to resemble both the angles of the printed bone, printed structure. Yes. So there is one video is also there. Yes. Can you play it? Cursor. Go down. No. Yeah, okay. So we're not able to play it. I don't know what is the problem. So this is actually we have set some parameters. Actually, that bone needs to be porous in nature. So we selected some parameters like there is only 15% density. We could have changed or altered it as per our requirements, or we would have gone through some simulations. But unfortunately, with some software errors and problems, we could not do that. Yeah, so actually what we could have done and which tools we could have used. we have the extension tool of ANSYS that's called Space Claim, where we can do these kind of simulations. Like we can go for the thermal, these properties we can know, and another is mechanical. So our problem is more into mechanical. So we were supposed to see the residual stresses and warpage effects and stress concentrations at different spots. But unfortunately, we could not do that. So at the end, I would like to say we got the model, but we could not run different densities and we could not test it using the simulation softwares. So I guess this is all on our side. Thank you. Thanks a lot. Did you try No, that simulation part we could not do actually. That space, yeah, printing is already there. We're having the space pen with this. This is 15% infinite density. But we got some defects, some layer defects are there in between. Yeah, here and printing speed was 60 and temperatures were 220 and 60. Okay, good. Thank you. Yeah, thanks. Yeah, please. Yeah, mesh generation, that is our own work. We need to, ANSYS has its own feature. ANSYS, ANSYS, it can be done, but this is the extension part of ANSYS. Space claim is the extension part of ANSYS. It is not means inbuilt. No, we did not do that because as I told, there were some issues with the software. Yeah. Otherwise, we could have tried we could have tried different densities. We could have run the simulations and we could have reached a conclusion like which density is best for our. Okay. Any other questions? Thank you. Okay. Thank you all. So now we'll break for a lunch. And then we'll actually meet at 2 o'clock. So I'll take one more session. Then we'll actually we can continue. Get the feedback. So please come back. Let's actually announce the winner of the starting. So you can go for the